Hello, class. I am back. As a matter of fact, I have switched books. I have run out doing all of the electromagnetic field theory lectures and everything else. I've actually run out of sheets in, I think, 2 books now, but both of these, I didn't use the whole book, of course. However, now I'm in a new book, and we've got a lot of pages here, so it shouldn't be too hard. And what I did was I've now expanded, since we went in the last lecture from the pictures to the free body diagrams, and we've seen what the reactive forces are that should go at various different support locations, right? This was a rocker, so it only stopped forces in the X direction. This was a hinge pin, so it stopped forces in the Y and the X direction, right? And I've broken down that force in the middle here into its 2 components, 6928 in the Y or vertical direction and 4000 in the and we've already partially solved this problem, right? So that's what I want to do. I want to start with where we left off in the last lecture. When we sum the forces in the X direction equal to 0, what that gave us was that B sub X equals minus 4,000 newtons, right? And of course, what that means is that we've chosen B sub X in the wrong direction, and that's what we would expect, because look at the force that's applied. The force that's applied is 4,000 newtons in the positive direction. So shouldn't B, I mean, if I was pushing the block in that direction, shouldn't B be pushing back against it? So there you go. We actually chose B in the opposite direction, but because we chose B in the positive direction in the first place, the answer we actually got is, what direction B of X would actually be working in, right? Okay, so that was summing the forces in the X direction. Then we sum the forces in the Y direction equal to 0 newtons, right? And what that told us was that A sub Y plus B sub Y equals 12,928, can't get this on here, newtons. I'm gonna have to extend into the other one. So that's what it told us. So we've got 2 equations with 3 unknowns, right? 2 equations with 3 unknowns. Because B of X isn't even in this equation. So we really need an equation that's going to get rid of some of those unknowns and help us out. So I want to now sum moments equal to 0. But what point should I sum the moments about? Should I sum them about the 3,000 newtons here? Maybe that point? Maybe this point in the upper right-hand corner. Because since it's a rigid body, the whole thing is going to be going. It doesn't matter where I actually sum them, right? But is there a particular place on this rigid body that I could sum moments about where the forces that are going through that point, or where unknown forces go through that point? Because let's face it, if a force goes through that point, right, then it can't cause a moment about that point. That's right. If a force goes through a point, it can't cause any motion, any moment around that point, right? Or any curvilinear motion. All right, so I'm getting ahead of myself on that one. But how about B? How about choosing point B, right? First of all, B sub Y goes right through B, doesn't it? And B sub X goes right through B. I have to give you some dimensions for this. This is going to be, this is 1 meter. This is 1 meter. This is 1 meter. I think everybody can see how this is going. this is 1 meter, and this is 1 meter. So all of these are broken up, and you know, if I wanted to, I could say this is 1 meter here too. They're all 1 meter increments in between the various different things here. So let's use B. Let's sum moments about B. You know, I forgot to turn on my thing. It's only been a few minutes, so let's see if I can put it about there. Okay, let's start that. So we've only been here a few minutes, and so I wanted to get the timer on anyway. So let's look at this then. So now I've got all of those, and of course, when we look at the distance between here and here is 1 meter, and the distance between here and here is 1 meter. So we can figure out the distance to all of our various forces, and we can figure out what the moments about B are going to be. So let's look at this 3,000 Newton force first, right? So if I look at that 3,000 Newton force, let's call that, I don't know, D1. And this other one will be D2. So just looking at that in comparison to B, I think everyone can see that I've got minus 3,000 newtons J. But isn't that passing right through B? Isn't By and Bx both passing right through B? Can't you see that the principle of transmissibility here, let's write that down. Principle of transmissibility. Now, don't get me wrong. I want to solve this. There you go. Principle of transmissibility, and of course, that's in your reading too. If a force goes here, then the force could be anywhere along that line being applied to that rigid body. So that's the principle of transmissibility. You can see it goes right through B, so there's not going to cause any moment about B. Because what is the actual R? Let's just look at the R from B to D1, right? Isn't that just going to be 1, 2 meters in the J direction, in the Y direction? So it would be 2 meters J hat. And then what is this? It's 3,000 newtons, right? So J crossed with J, right, is going to give me 0, right? Anything crossed with itself. So J crossed with J is going to give me nothing. So that really is giving me nothing as far as the moment goes. In fact, let's just look at the positivity and negativity of all of these two-dimensional moments. Don't get me wrong. When we go to 3 dimensions, we're going to have to really use our understanding of, and I'll be doing it here too. But I think everybody can see that only parts of our radii or our distance vectors are going to be used, right? Just the I parts are going to be used, and we, except for the 4,000 newtons, of course, that's working that direction, and then the J part of that distance vector is going to be used, right? We'll call that point C. All right, so let's just figure out what all of our moments are just very quickly. Let's just see, right? So we don't have any of those. And if we did look at our moments, this 3,000 isn't going to cause a moment about it. How about the 6928? I'm just going to write these out. This is the first moment. It's going to be, I'm going to put the magnitudes here, 6928 newtons, right? And then how offset is that? 1 meter, 2 meters. So 6928 newtons. And is that going to cause it counterclockwise or clockwise rotation? I think everybody can see that it's going to be counterclockwise, so it's going to be positive, right? So times 2 meters. That's our first moment. That's this moment right here. How about this moment right here? Isn't that going to tend to turn it clockwise? so it'd be a negative moment. So minus 4,000 newtons times 1 meter, right? That would be our second one. That'd be the 4,000, and that's offset by 1 meter that's tending to cause it to go clockwise. How about this 3,000? Isn't that tending to go counterclockwise? So that would be a positive 2, and that would be 3,000 newtons. And then how far off am I? 1, 2, 3, 4. 4 meters. Right? Counterclockwise. Do we have any more? Yeah, we've got a sub y, don't we? A sub y, now that's going to be tending to cause it to go clockwise. So it would be minus a sub y times 1, 2, 3, 4 meters. And we know that that all equals 0. Oh, got to dip into that next column again, don't I? I'm not going to put newtons, Newton meters, I mean. I'm just going to put the 0. So what this gives us then is an equation whereby we can solve for a sub y, right? The only unknown in this equation is a sub y. So if I were to solve this equation, let's just figure out a couple of these. So 2 times 69, 28. 2 times 69, 28. Oops, forgot to turn it on. 28. 13,856. 13,856. All right. Positive, and then minus 4,000, and then plus 12,000, right? And so if I've got minus 4,000, that gives me 9,856. And then plus 12,000 gives me 21,856. Let me just do that. 21,856, and that's going to be divided by 4 for us to get a sub y. Right, so 21,856, and then divided, that of course would be Newton meters or joules, and then divided by 4 meters, and that gives us a sub y. 5,464 newtons. You know, now that we know a sub y, we can immediately figure out what b sub y is, can't we? Well, actually, I'll write it right down here, b sub y, because we already know what b sub x is, minus 4,000. So we can figure out what b sub y is too, because we know it's just the difference between this, a sub y, and 12,928. So 12,928 minus 5464 equals 7464. Is that right? Yeah, I guess that is 7464 newtons. Interesting, just the 464 repeating itself there. I'm assuming that's just a coincidence. I don't know why or how else it, you know, because it certainly isn't the first significant digit at all. So, AY and BY equal 12,928. And that is exactly right. And then B of X is minus 4,000 newtons, right? So we've got all of our principal characteristics, all of our forces, our unknown forces, by using our free body diagram and static equilibrium equations, haven't we? Now let's go over here and do this too. And I think everybody can see from this that really the distance here to 2 meters is the only thing that matters. We could say that, okay, well, this would be, you know, at the centroid, since this is the center of gravity. That's the center of gravity. This 9,800 newtons would really be there, and we don't know exactly how high it is and everything else. But it doesn't matter. It doesn't matter how high up it is or what the R value is, because it's only this component, and this is the only component of the weight, because the weight is working toward the center of the Earth, right? So we know, and we also know F sub W is 23,544 newtons. So we can do the same thing we've got here. First of all, let's sum the forces in the x direction equal to 0. So I think everybody can see that means that A of x plus B of x equals 0. What we're really saying there is that A of x equals minus B sub x, right? That's what we're really saying. So that's our first thing. So summing the forces in the y direction equal to 0. Now, well, we've got A sub y, right? That's in the y direction, minus 9,810 newtons, minus 23,544 newtons, right? And that has to equal 0. So that tells us that A sub y equals 9,810 and 23,544. And that comes out to 33,354. 33,354 newtons. So we know what A sub y is going to be. We don't know what A sub x and B sub x is. And how can we get rid of most of those? Well, we could sum the forces, sum the moments about A, right? And we're doing it about A because A, we can get rid of A sub x and A sub y at the same time, right? So when we look at this now and we look at what the moments are about A, we can see that the only thing that's really going to matter is the distance here, the distance in the x direction, because all of our forces are in the y direction. So we can see that if we're taking this is going to be a negative, right? So negative 9,810 newtons times 2 meters. Then we've got another negative one there. So that's make sure that's a negative. And then we've got another negative one there that's going to be minus 23,544 newtons times 6 meters. Right? And then we've got a positive one, or actually we don't. We've got another negative one, oh wait, B sub x. B sub x is going to be a positive. So positive B sub x. And how far is that off? That's off perpendicular to the application of the force, 1.5 meters, right? And that's got equals 0. And so what you can see here is that we now have a equation with B sub x in the equation. We've got A sub y. We know what A sub x is in terms of B sub x. So now we can figure out what B sub x is, because this is a positive, this is a negative, this is a negative. So 2 times 9810 plus 6 times 23,544 1,335,44 equals 160,884. So 160,884 joules or Newton meters, if you want to think of it in those terms, divided by 1.5 meters gives us 107,256 newtons. So that's what B of X is, and then we know A of X, right, is going to be minus 107,256 newtons, right? So there you go. All right, so now we've used static equilibrium and our summation of forces in the x direction, summation of forces in the y direction, summation of moments about a point, and we've chosen our points judiciously to get that. Now, what I want to do is I want to look at the last one now, which actually, now that we've done those two, is probably easier than both of those two. But let's look at this and see what the forces are and the moments and everything else. And I think everybody can see that summing the forces in the x direction equal to 0 tells us that A sub x equals 0. Right? Because there's no forces pushing back against it. So our reactionary force A sub x is going to be equal to 0. But not A sub y. Right? A sub y is going to be the opposite of this. I'm just sort of jumping to the endpoint now. I'm not doing all the summations because you are looking at this just like I am now, right? So A sub y, though, is going to be 800 plus 400 plus 200, so 1,400 newtons. So there you go. We've got A sub y, and we've got A sub x straight off the bat. But now what we need, because these moments aren't going to sum up, we need a reactionary moment, right? We need some type of reactionary moment to sum these all up. So we know that the sum of the moments about, I'll call that A, about A, are going to be equal to 0. So let's do that. So we know we've got a negative 1 here. That's a negative 800 newtons times, I should put the distances on there. This was, God, 1.5 meters to there, and then 2 meters there, and then, or 2.5, God, 2.5 meters there, and then 2 meters there. So the first one here is 1.5 meters. So that's what I'm going to put in, 1.5 meters. And we know that's negative because it's going clockwise in this two-dimensional world. And the 400 meter one, well, that's -2, isn't it? It's going clockwise. So that's going to be 400 newtons times 2.5 plus 1.5, so 4 meters. And then let's do the 200, and that's also going to be minus, right? It's making it go clockwise. So 200 newtons times 6 meters, right? So we've got all of those. And then we've got this as a plus the reactive moment, right? And so, and all of that altogether is going to equal 0. So what that tells us is that our reactive moment is going to be positive, right? Because this is going to stay on this side of the equation, and all of these negatives are going to go to the other side of the equation. And so I've got 800 times 1.5 plus 400 times 4 plus 200 times 6, and that equals 4,000 joules or Newton meters, if you wanted to think of it that way. And it's going to be in the direction I've drawn it. It's positive. So I've assumed that it was positive, and I'm correct. The reactionary moment against all of those applied moments is positive counterclockwise and is 4,000 Newton meters or 4,000 joules, right? Does everyone see how I got all of those various different things? You know, I think I'm going to grab a red pen. I'm just going to mark out some of these. There we go. So we know exactly what we did. We've actually come quite a long way in looking now at going from pictures to free body diagrams to using static equilibrium to solve those free body diagrams. So that's good. All right. We still have some time, but I'm saying, you know, we've finished up this area. We're going to go on to something that's I couldn't say more interesting, but similarly interesting. Let's say that. Okay. See you at the next lecture.